Hello and welcome everybody. Thank you for joining our new Cards Digital Thursday webinar. The topic today will be how to discover better designs faster. First, let me shortly introduce myself. My name is Vasco Keizer and I've been working at Cards for nearly 5 years now. I mainly have a commercial role in which I focus on sales in the Benelux for the simulation portfolios that we as Cards represent. That being the SimCenter portfolio and the Moldex 3D portfolio for injection molding analysis. I have a background in automotive engineering and my technical expertise within Cards is the SimCenter 3D portfolio. And joining me today once again is Florian Vesting from the company Volupe. So Florian, if you could shortly introduce yourself as well.
Thank you very much, Vasco. My name is Florian Vesting. I am in the technical support team here at Volupe. Volupe is also a Siemens partner, particularly for the Nordic countries and Benelux countries. We are also a Platinum Smart Expert partner for SimCenter StarCCM+. So my background is from the marine side. So I have done my PhD studies on computational fluid dynamics and optimization of ship propellers. And I've been working with CFD and optimization for about 12 years. And here at Volupe, I do the support for SimCenter StarCCM Plus and Heats, and also partly on AimSim.
Thank you, Florian. Taking a look at the agenda for today. We just finished the introduction, so we're going to start off with how design space exploration can help you to drive innovation. Then we're going to take a closer look at how you can set up a design space exploration process with Heats and what insights that can bring you. And in doing so, we will also be showing you several demonstrations of the software as well. And at the end, we will give a couple of examples where companies have successfully used Heats in the past. Now to start off, the reason we're talking about design space exploration is because we want to drive innovation. 83% of Fortune 500 CEOs list driving greater innovation as one of their top 3 priorities. But although everyone wants greater innovation, many are unsure on how to achieve it. Now today we will specifically be looking at how you can get more value out of your modeling and simulation environment, while at the same time drive your innovation. The example on this slide perfectly describes the complexity of many of our products today and the challenges that engineers are therefore faced with. This example of a cooling simulation from an electronic box shows a multitude of variables which an engineer can play with in order to achieve the most optimal design. There's the type and location of the fan, the size and location of the air holes, the material, location and dimensions of the heatsink, etc., etc. Now, of course, an engineer can run a simulation, interpret the results and based on that change 1 or 2 variables in hopes of achieving a better performing model. However, due to the amount of variables and how they each affect each other, it is almost impossible to explore all the design options and find the best possible solution. This is where design space exploration comes in, and where the software automatically alters the variables, runs the simulation, interprets the results, checking whether it's a feasible or infeasible design, and continuously improves the design further until the best feasible design is found giving the set objectives, which in this case is a minimum temperature and mass. Now this is a process which can run in the background, overnight or over the weekend, while the engineers focus on other tasks, resulting in this specific example in both a reduction in mass as well as a significant cooling improvement. Of course, this is a specific CFD example, but the same can be done for the type of simulations that you are currently running, whether that is structural or acoustic or even logistical. The goal of utilizing design space exploration is to move beyond the standard use of simulation for validation or troubleshooting. Of course, with simulation-driven design, as we presented in a previous webinar, we are already moving into the proactive domain, as we are already trying to use simulation as early as possible in order to have a maximum impact on the costs, quality and time to market. And this is also where most companies nowadays are operating. But the real value lies in automating the simulation process so that the engineer has more time free for other activities, and then to explore broader design spaces to discover much better designs in a much shorter amount of time. Now I would like to give the word over to Florian, who will talk a little bit more in depth about the process of setting up a design space exploration run with heats and how to interpret the results. Florian, if you could take over the presentation.
Thank you, Vasco. So let's discover better designs faster with heats. Here on this slide I have a typical setup for prototype development. You have design variables that you can change. You do some testing and simulations and virtue testing, and you get a response out of it, which is something that you care about. Ideally now you would actually be satisfied right away, but this is not often the case, so you have to do some modifications, go back to your design variables, do the testing again, and look if your modifications now meet all the requirements. So when we ask people how they actually spend their time on this process, they say often that they use a lot of resources to build the model, test it, and then when it comes to improvements like design modifications and the assessment, often the project runs out of time. But we can all agree on that the actual value that you can extract is exactly here lies in the improvement of the design and not in building the setup. So this is what Heats actually wants to do. It wants to align the values better with the time spent and the resources required. And therefore Heats comes with three main pillars. The first is process automation that allows Heats to run most of the CAE tools right out of the box. You can just drag and drop them into the interface and execute those models and connect them together. You can, the second one is distributed execution. You can use your computer resources in the best possible way and use cloud-based or on-site or off-site resources. And then the core is Heat's efficient search algorithm, the best on the market actually, that allows you to be confident in finding improvements and with any given number of variables for your system. And the last one is that you actually can make discoveries and get extract meaningful data and make based on that intelligent decisions. So in today's webinar, I would like to show you a study based on this 4 key enablers for underhood pipe flow design. So this is the engine, and here we have a pipe connection between these two hosts here. Inlet is on this side, the flow goes in and it goes out here into the rest of the engine. The pipe has some parameters. It's built up from inlet, outlet, and in between we have 2 cross sections, circular cross sections, where you can vary the diameter and then the position of the 2 cross sections. So you can change it like this and up and down as well. And if we look from the side, for the second circular cross section, it lies about here. We can also tilt the cross section with an angle. So the idea is to actually maximize the flow uniformity here at the outlet, while at the same time minimizing the swirl. To do that, we use 2 tools to simulate and understand how the virtual prototype actually performs. One is NX for the cut geometry generation, and one is StarCCM Plus for the simulation. So in NX, we prepare the design with parameters to describe it, and then Heats comes in and overrides these parameter values with design variables which were created or controlled by the algorithm. On the other hand, on the other side of NX, we actually take the new generated geometry and put this new geometry into our star analysis simulation and exchange our pipe part inside star with the new surfaces, and then they get updated and meshed, and we have new boundaries. So heat controls this in an automated way and iterates to improve the design. Here we can see how we can build it up. We just drag and drop the portals into the place, and we can also use the default portal and just assign it to a certain program. Like in this case, we might want to have a third program, maybe SimCenter 3D for strength calculations, and then we can move them around in the design. The processes can be moved around in your work on your desktop here, and decide if you want to run it in parallel or if they are dependent on each other. So you can drag and drop any other portal here as well. So for this case, we just have NX and star, and then we need to define the parts. So we need to have a basic setup with the part here as an input to our analysis and an output. We use a parasolic here, and the same for star. We have as input our baseline design, and then we need as input as well our new pipe part that comes from NX, and then we have output as well, and here we tell heats actually to exchange the pipe part in star with the output that come from NX. Then we create design variables, we create responses, then we go to tagging and actually connect our input files and output files with the design variables and responses that we want to have, like for in this case the flow uniformity from a report in SimCenter Star. So you actually don't need to have any manual data transfer and no custom scripting. It just automatically shares data between the different modeling and simulation products, and ensures that in this manner it robustly remeshes and updates the simulations, so that you can spend your time more efficiently on the post-processing and save some time in the actual setup here. So the next enabler is distributed execution. In this case, I actually use heats on my local machine together with NX on the local machine, but I tell heats that I want to run the actual CFD analysis on a Linux workstation, which is located remotely. But you can use, as I mentioned before, cloud computing or any other cluster resources that you have at hand. And you do that by, for your process, you select from the drop-down menu which computer resources you want to use, one execution of NX, and on the cluster head node, I run 2 simulations of the CFD analysis in parallel. And we have kind of a powerful cluster, so I go to the star portal and also select that I want to use the power session and 40 cores per job at the same time. So this actually enables you to leverage all the available computer resources in the best manner and reduce the simulation turnaround time significantly, so that you can maximize your investment. Next is the efficient search. We have direct search technology here enabled in the Heat's Sherpa algorithm. It works without the need of surrogate models or anything else. You don't need to screen your variables for the importance, because that does Sherpa on the fly actually updates and adapts and combines the best search strategies. So how does it look? You go into the study tab, and then you can select what study type you want to do. You can do more than just optimization. You can do a robustness and reliability analysis or design of experiment. But we will stick with an optimization, and we want to have a multiple objective optimization. So we need to go to our responses and specify that objectives that we want to have. The flow uniformity should be maximized, and the outlet swirl should be minimized. Once you started your simulation, you can get information on the fly, which output you get, which variables are created. So at the beginning they're quite distributed quite evenly. You see which designs already came back from the simulation and with success, and which are under investigation, and you can see how much time the simulations actually took. So for the CFD, we had about 2 minutes, 1.5 to 2 minutes for the simulation there. So this is very, very powerful, and you don't actually need to be an optimization expert to set this up. You just specify how many variants you want to run based on the budget that you have on time and resources. And Heat's Sherpa algorithm adapts the search doing the fly and speed up the overall optimization time. So, but you can also tell Heats and let Heats learn from previous simulations, such that you restart your optimization from a design of experiment. Then it already got some knowledge and can make use of that. Last but not least, most importantly, actually, is the enabler number 4 to get insight and discover the designs. So you can build up your dashboard with your screens, multiple plots, and visualize design and trends more comprehensively. So you can here we see the Pareto front of our flow uniformity and our outlet swirl. And in that plot, we can go through all the variants, click on them, and see instantaneously how they actually perform from the figures. Or you go through a design table, and you already noticed that there is a jump in the data here, which is an indication for 2 separate families of designs. And this can be very interesting to actually decide or determine which of the design families works best then, depending on manufacturing, packaging, or something like that. So when you are in Heat's post, you can do more than that. You can, for instance, look at the parallel plot. If you're not familiar with the parallel plot, you see here we plot on vertical axis the performance and the parameters, and for each variant that is created, we connect the lines across these vertical axes. And what I intended to show here is actually that how you can make better visualizations of these 2 families. So I created a subset of both the lower and the upper designs, and then I load these designs in my parallel plot, and then I can make some highlighting where actually these designs are located, so that you can go and see instantaneously, okay, this family follows such design variables, and the lower family follows actually another variable, like for the Y1. But you can also go through all the figures itself and make some some animations out of that as well directly from the Heats user interface. But you can do more. You can also do some importance analysis, like in this plot here. Here we have the flow uniformity and the outlet swirl, and the performance, the importance analysis tells me that, okay, for the uniformity, I actually have 2 to 3 design variables that are important. Most importantly is the diameter 2. But when it comes to outlet swirl, actually all of my variables are important and have influence on the outlet swirl. So, and then you can do also a correlation analysis, which of the parameters influence which of the objectives. So this actually enables you to get knowledge about the design performance and get deep insight in your product design alternatives as well. And thereby Heats makes it very easy to extract meaningful data and make intelligent decisions based on that. So here we have an example of Trek, a bicycle designer who used design exploration to come up with a new frame design. The goal was to minimize the aerodynamic drag and minimize the frame mass at the same time. So they used CATIA Abacus for the strength and stiffness and weight calculation, and then they used star CCM Plus for the drag calculation and did a variation on optimization, and this resulted in simultaneously reducing drag and weight and provided greater design insight. Here's another example from the same bike manufacturer, which is optimizing the position of the biker team to reduce the aerodynamic drag. So they moved around this in star moved around the position of the bikers in star and calculated the drag to find the best possible configuration. And one more example, maybe, why not improve the recipe? In this case, the idea was to reduce costs by providing a certain amount of nutrition and moisture and proteins and so on. And with that, using Heats, getting more understanding of how this design variables, which were like the ingredients, work together, and they could reduce the costs by almost half of it. So thank you very much. I hope you find this very interesting.
Yes, thank you, Florian, and thanks everybody for joining today. Please do not hesitate to contact us if you have any further questions, and I wish you all a nice day.